Today I'll be talking about fully managed OSS compatible lakehouse with BigLake Managed Tables. So, first I'd like to thank OSACon for the opportunity to speak and everybody in the audience for attending today. In this session, I'll briefly touch on lakehouse architectures and what they are. I'll discuss BigLake, how it's evolved over the last couple of years, and how it moves us in the direction of open source lakehouses. And then I'll focus on the main topic of today, which is BigLake Managed Tables. We'll look at their benefits, how they contribute to the open source lakehouse, how they work under the hood, and then I'll move on to a demo. At the end, we'll get some next steps so that you can get hands-on as well. So just to introduce myself, I'm Jeff. I'm a developer advocate here at Google Cloud, and I focus on all aspects of the analytics stack, but spending most of my time on data warehousing and a good amount of time also making sense of unstructured data. Before Google, I worked as a data engineer at a large number of media studios here in Los Angeles, and I spent that time as a data engineer involved with a lot of data warehousing, data lakes, lakehouses on Google Cloud, on AWS, with other technologies here and there. So let's just kick off how we got to Lakehouse. And just as a disclaimer, I'm not going to go into the entire history of warehouses and lakes in this talk. There are plenty of wonderful talks on the topic and probably a few at this conference. So that said, if we go back to the days where data warehouses were new and novel, and they were essentially OLAP databases used for BI and reports on your structured data, the kind of days of Teradata and Netezza, and then came the early 2010s with the rise of data lakes, where developers realized that they could store all types of data in object stores, cheap object stores like GCS or S3, ranging from unstructured data to their semi-structured JSON and logs to structured data in their format of choice. And they could start running open source analytics on top of this data using tools like Hadoop, Spark, Presto. And suddenly there was a lot of flexibility on the data lake side compared to the enterprise data warehouse. Data lakes resulted in some really incredibly useful design patterns because they taught us there were new ways, new analytics use cases that data warehouses were not equipped to handle. For example, building an AI ML pipeline can sit on top of a data lake, but was a lot harder to do on top of older data warehouses. But as the data lake, made up for some of the shortcomings on the data warehouse side, they still had their own issues. For example, you can imagine that lakes often didn't have enterprise features that companies would expect to build on their analytics platforms. Think things like fine-grained security or auditing or predictable performance. Many of these were missing from data lakes in the early days. And as we went forward, large enterprises began to use both, like an enterprise data warehouse and a data lake, to fit their use case. But they wanted enterprise features across both systems, and they wanted them connected. So a data lakehouse merges these two approaches, a warehouse and a lake, to create a single structure that allows you to access and leverage data for many different purposes, from analysis to BI to data science and more. And data lakehouses capture all of your organization's data, whether that be unstructured, semi-structured, or structured data. They store it in low-cost object stores while still providing the enterprise capabilities for all users to organize, explore data according to your or their needs. And pertinent here too is the idea that your lakehouse can store data in open source file and table formats. You're not locked into a proprietary warehouse format or a single query engine to access your data. You can use different engines. You can use different file and table formats, whether they be proprietary or they be open source, like Spark for machine learning workloads, Flink for real-time processing, whatever it may be. And what does this look like in practice? Well, as a developer, you should have a consistent user experience no matter how you access the data, from a UI, an SDK, an API. And you should have a choice of your analytics engine that you use across that data. The engine can sit on top of open table formats like Iceberg, Hudi, Delta Lake, or they can just access the files directly in the object store, in a low-cost object store of your choice, and in a variety of file formats, be that Parquet, JSON, Avro, whatever it may be. Lastly, there may be an optional layer of data discovery, cataloging, lineage, orchestration that can span your entire data stack. So given this simplified lakehouse architecture, let's see where we are with BigLake. How does BigLake fit in? And to understand BigLake, it's important to think about, where did it come from? Well, BigQuery offered and continues to offer tables with enterprise features that you'd expect from a data warehouse. That includes fully managed, table experience, fully managed table experience with performant queries, fine-grained access controls, streaming inserts, automatic reclustering, etc. With BigQuery tables, we use an internal proprietary storage, and an internal query engine, which works great for many use cases. But we found that we quickly heard from engineers that they had data stored in other places and in different formats. For example, they heard from the marketing team on the second floor that they had a CSV stored in a cloud storage bucket that would provide a lot of value if we could just join it to what's in the data warehouse. But the team on the second floor couldn't get the data into the data warehouse. So as a result, we built BigQuery external tables. And with external tables, developers could now access data in object stores or other places. They didn't need to store their data in a proprietary BigQuery format just to query it. However, these tables were read-only. They didn't have fine-grained access controls, and they didn't have some of the enterprise features that BigQuery tables did. BigLake tables. With BigLake, developers could continue to store their data in open file formats like Parquet, CSV, Avro, whatever it may be, and apply open table constructs like Iceberg on top of this data. So the data no longer needed to be stored in Google Cloud Storage either. It could reside in S3 or Azure Blob Storage. And querying wasn't restricted to Google's Dremel engine any longer either. We could use that, or we could use open source engines like Flink or Spark on top of that same data. Now, BigLake also introduced a new API to access this data. And if developers queried the BigLake APIs, they could also enforce fine-grained access control like row or column level security over the data in their object stores, which was traditionally difficult to achieve. And this is really where we could start to offer that lakehouse architecture, giving developers the choice of data and file formats stored on their choice of cloud object stores, a choice of query engine, and the enterprise features that their company might expect from a more traditional system, like predictable query performance, security, data governance, etc. However, BigLake tables are still not managed, meaning that a data engineer still needs to ensure that they're writing data at the proper file size, that there's a logical partitioning strategy in place, etc. And this is where BigLake Managed Tables arrives. So BigLake Managed Tables builds upon BigLake tables and offers many of the same principles of a lakehouse architecture, like open file formats, open table formats, support for open source query engines. But as the name suggests, the tables are managed for you. You don't need to worry about file sizes, clustering, remembering like how to snapshot or anything about snapshots for your Iceberg tables, or really much else. We'll dive deeper in the next few slides. Now, BigLake Managed Tables allow you to keep your data in open file formats like Parquet while allowing querying via analytics engines, both open source and BigQuery. The tables are designed to act and feel similar to BigQuery native tables and even offer some of the traditional data warehouse features you might come to expect, like the ability to write DML operations, fully managed background optimizations for performance and cost, high throughput streaming, time travel, schema evolution, etc. So in short, BigLake Managed Tables combine the benefits of BigQuery table native infrastructure with the open formats and cost benefits of storing your data in an object store with a fully managed experience. Now, to drill down on a couple of topics before we look at the architecture and how this works under the hood, using BigLake Managed Tables, you can create tables on your Parquet data or read and write to that table using OSS engines or BigQuery alike. Not only this, but BigLake Managed Tables support high throughput to tens of gigabytes per second, and that data is instantly queryable as soon as it's written. So there's no more trade-off between freshness and performance, even with Iceberg tables. Lastly, you can execute large-scale DML, so operations like inserts, updates, deletes apply to underlying Parquet, and BigLake Managed Tables takes care of all the Iceberg snapshotting on the side. So we're bringing all of the knowledge and experience that we have running BigQuery managed storage, which again is a multi-exabyte system. And we're applying all of that experience to objects stored in your storage buckets with BigLake Managed Tables. And this translates to a fully managed experience on your open data. For example, Parquet files that underlie your tables are automatically managed. They're resized to fix that small file problem that occurs when you're, say, writing millions of tiny files that are costly to query, costly to resize, and costly to expire old Iceberg snapshots. Instead, BigLake Managed Tables resizes the files for you. It also reclusters the data so that your queries execute in a more performant manner. If you delete data from your tables or you have snapshots that expire, automatic garbage collection will delete those files from the object store too, which saves you money on on your cloud bills, and also saves just general storage space in your buckets. BigLake Managed Tables also automatically writes snapshots periodically, so there's no need to worry about managing or expiring old snapshots. Lastly, on security and performance, which is paramount to many of the people we've spoken with, whether you're using BigQuery or an OSS engine like Spark or Trino, you can be rest assured that all security and governance you have in place for things like row and column level security are always enforced. There's zero trust on the query engine. Security is always pushed to the BigLake runtime and enforced by the API when you access your data. We also provide predictable performance. So if you're streaming data to a BigLake Managed Table, you can query that data the moment that it's acknowledged. You don't need a microbatch. You don't need to write compaction jobs that clean up or combine small files. You don't need to worry about expiring snapshots while streaming. These are all common concerns when you're using Iceberg tables. And we'll discuss why and how this works when we look through the architecture. So when thinking about the life cycle of a query, there's two ways that we can access our BigLake Managed Tables. First, we could submit a job to the BigLake read and write APIs. When we do this, the data goes to a query coordinator, which handles the query by accessing a transaction log right down here on the left side. And the transaction log is going to tell the query coordinator exactly which files in an object store should be read from or where they should be written to, depending on if it's a read or a write job. Batch and streaming jobs also take slightly different routes, where batch is written directly to cloud storage in Parquet format, and streaming jobs actually are written temporarily, the tail of the table is written temporarily into a write optimized storage, and then output into Parquet in your object store right afterward. A benefit of using the BigLake APIs or this approach is there's strong consistency and fine-grained access controls that are enforced at runtime. Additionally, a user could access the data using Iceberg snapshots themselves, which is here on the right side. These snapshots tell the open source engine which Parquet files make up a table at any given point in time and allow the query engine to access the correct objects. On top of all of this, you see some of the other goodies that are provided, like clustering, file compaction, adaptive file sizing, garbage collection, etc. But regardless of which path you take to access a table, BigLake Managed Tables should look and feel similar to BigQuery native tables because there's a lot under the hood to make that happen. Now, again, the managed part of BigLake Managed Tables also includes exporting metadata to Iceberg snapshots. So the exported Iceberg snapshots are registered to a BigLake metastore, which provides an Iceberg catalog implementation so that open source query engines like Spark or Trino or Presto or whatever it may be can access these data directly as Iceberg tables. And just to reiterate, again, there are two paths that someone could take to interact with these tables. First, using the BigLake APIs, where we provide built-in connectors for different engines. Take Spark for an example. Spark would use a BigLake connector to hit the BigLake storage APIs. And the advantage again here is that you get strong consistency and you can apply fine-grained access controls here because the BigLake API layer enforces things like row or column level access controls or data masking. The other approach is to access Iceberg tables directly from an object store. So the query engine would discover the Iceberg snapshots from the BigLake metastore and then read the data directly as Iceberg tables using some sort of open source Iceberg library. Now, as we mentioned earlier, we can stream tens of gigabytes of data per second to BigLake Managed Tables and query them immediately. So let's take a look at how this works. When an open source engine like Spark, Flink, or Beam starts writing data to a BigLake Managed Table using the write API, the tail of the table is written to write optimized storage called Colossus internally. And the data is temporarily stored in Colossus and quickly converted into Parquet files. However, if a user queries data that's streaming into a table, they get basically a union of what's in Parquet and what's in Colossus. So there's no lag, right? You can get a true view of what data has been streamed in at any given point in time. This means there's no need to microbatch your data. There's no longer a trade-off between the freshness and performance that typically comes with writing a lot of small files. And there's no need to think about cleaning up your Iceberg snapshots. Things work seamlessly, and we'll show an example of this in just a minute. So take a somewhat fictitious but realistic scenario where my team lead comes to me, and I'm a data engineer, and they ask me, hey, Jeff, can you create a new table? And this table is going to contain real-time telemetry data for IoT devices in our taxi fleet. For example, that might include latitude, longitude coordinates of any vehicle, the taxi meter ticker price for every second, et cetera, right? We're getting all of this real-time data. And our team is committed to open principles. We want to store data in Parquet. We'd like to put Iceberg tables on top of this so we can query it using Spark. Well, being a good, good in the corporate world, or just be bad at saying no to things, I say, yes, team lead, I will do this for you. And I don't give it much thought. But I instantly begin, as my team lead walks away, I instantly begin to think about the maintenance of these Iceberg tables. How am I going to get this done? Just to keep my Iceberg tables performant, there are all sorts of items that I need to consider and keep up with over time. Some of the commands are in here for the Spark implementation. Just to begin, what is the target file size? How large should these Parquet files be? How do I determine this? If I get this wrong and the data changes, how can I combine smaller files into larger ones to reduce the metadata overhead and improve runtime performance? When should I be rewriting my manifest files? How do I expire snapshots? There's a lot to think about that just comes to my head after I've said yes to my team lead. Instead of worrying about each of these config parameters, I'm just going to use a BigLake Managed Table, because BigLake Managed Tables cover all of this for me. The target file size and auto compaction of those files, the garbage collection for files and snapshots. The streaming data is immediately available, right? This is all super helpful with high throughput data. I don't need to worry about microbatching or worry about these other config parameters any longer. So let's take a look at a demo here. Now, in this demo, I'm in the BigQuery console. I'm going to create a table, and this table is a BigLake Managed Table. You see some DDL here for the table. Just also note that this is what we're calling the green table. These are green taxis. We'll get to yellow taxis in a minute, but these are green taxis for a BigLake Managed Table. When I create this table, I also have, I get to define what is my file format, my table format, and where should that data reside in cloud storage. So I'll create this table, and I'll show you that there's nothing in the table. So we should have a count of 0. We do. And if I go over to my cloud storage bucket, refresh it, there's nothing in here, right? There's no Parquet files in my cloud storage bucket. What I'll do next is load data into that BigLake Managed Table that I just created. So we can see that the data was loaded into the managed table. I can select account, and we'll see, 9.8 million records were inserted into this table. Now, if we go back to cloud storage, refresh it, we should see, okay, there's a data prefix, and under this, there are there are Parquet files that were just written, and they all have approximately the same size because BigLake Managed Tables has determined what file size should be used. If that changes over time, things will be rewritten, but this is the initial file size. We see that there are 43 records down here at the bottom right, 43 objects rather, in our bucket right now. So if I were to query this table, as I just did, it's accessing those Parquet files. I'm then going to update this table. So this table doesn't tell you what company, which taxi company we're referring to. And this is the green taxi company. So I'll add a column called taxi company, and I'll set the value for green for all of these records on the table. I'm then also going to see it modified all 9.8 million records. And I'm also going to delete some of the outliers what I think are outliers in the table. So delete the fares that are greater than 1,000 or that are less than $0. So this removed 28,000 records from the BigLake Managed Table. Now, if I go back to my object store and refresh, we see there are new files. So we see there are 93 files now. So I think that bumped up the number by 50 objects here. And we see there are now objects, Parquet files with different sizes. And the idea here is that because we modified the table, there are now new files written out to our object store. When I query the table now, if I were to query the table, it would take, BigLake Managed Tables knows which files to access, and we'll show that here. When I query for the records with a total amount greater than 1,000, there's no data to display because I've already deleted those. But if I use some time travel and said, actually give me the records as of 2 minutes ago, BigLake Managed Tables goes, hey, let's look at the files in the object store for 2 minutes ago. What did the table look like 2 minutes ago? And it gives me some of the records where the total amount was greater than 1,000. Now, over time, these snapshots will expire, and these files will be cleaned up via a garbage collection mechanism automatically. I think the default right now is set to 7 days time travel expiration. So another thing we can do that's pretty unique is union or combine BigLake Managed Tables with standard native BigQuery tables. So here we have yellow trips, yellow taxis are all represented in a standard or native BigQuery table. And again, we have our green taxi trips, which is our BigLake Managed Table. We can put them together, query them, and we'll just show that they combine nicely together when we union them. Now, this isn't super exciting, but what becomes more useful is when we run some analytics on top of this. So we'll union the tables, and then we will sum the total fare for the year 2022. And we get the results that green taxi had about $1.3 million in fares, and yellow had 4.7 million in fares in 2022. Now I could take this query and I could also, write this. I could put this as a Spark SQL query, run it as a Spark job, and I will get the exact same results. Right now, I'm just showing how to do this with the BigQuery query engine, but again, this could be done using other methods as well. Now, going back to the high throughput scenario that we talked about a second ago, where my team lead said, hey, Jeff, I'd really love for you to create a table for our IoT devices and our taxis. This is where I'm going to do it. I create a new table called BLMT real-time. Again, I define the file format, the table format, and where I'd like the data stored as Parquet. I've already created this table, and I'm actually streaming data to it right now, so I won't recreate it. But I can check what the result, what are some of the records that are being input into this table. Things like a ride ID, latitude, longitude, timestamp, meter reading and its increment, So there's a lot of data streaming to this table, and it's streaming in via an Apache Beam job that's streaming in a number of records per second into this table. So what that means is when I run some aggregate function on this BigLake Managed Table, I should get a result. So we're getting the sum of the meter increment. So we're just going to call this the sum of fare. And we divide it by 1,000. So it's really $562,000 in taxi fares as of right now. If I were to run this again, I should get a slightly higher number as the fares have continued to increase as we stream more data in. Right now we have 563,000. And if I were to keep running this, that would continue to increment up because we continue to stream data into that BigLake Managed Table. So the idea here is that part of this table is already written to Parquet in cloud storage. And the other part of this data that's streaming in literally this second is probably still in our write optimized storage. And when we run this query, it's concatenating all this data, it's unioning the data together and running an aggregate amongst all of it. So there's no delay in this real-time streaming data. So that's what I have for the demo. If we move back to the slides, I just want to thank everyone who's made it this far, first of all, and leave you all with a couple of resources to get started. So first, BigLake Managed Tables is still in preview. So there's a sign-up form to request access, but please feel free to send access through for yourself, for your friends, anyone you'd like. Liberally use this. We're eager for more people to give BigLake Managed Tables a spin. I've also included a little bit of documentation and given an alias for a Google group that we have internally. If you have any questions, you can hit up our engineering team and they'll be happy to talk to you there. Lastly, I've included a demo video, a little bit of a longer form demo in case you're interested in checking that out.